Look up at the night sky on a clear evening, far away from the glow of city lights, and you might see a faint, fuzzy smudge in the constellation of Andromeda. To your eyes, it looks like a small cloud, a quiet neighbor in our cosmic backyard. But that image is a ghost. The light hitting your retinas right now began its journey 2.5 million years ago. To put that in perspective, when those photons left their stars, modern humans didn't even exist. Our ancestors were still sharpening basic stone tools in the African savanna. Andromeda appears like a nearby neighbor on cosmic maps, a sister spiral to our own Milky Way, sitting approximately 2.5 million light-years away. But don't let the maps fool you. Even light, the fastest thing allowed by the laws of physics, needs 2.5 million years to cross that gap. So, what would happen if humans actually tried to bridge that distance? We can see Andromeda with the naked eye, but reaching it may be one of the most impossible journeys in the universe. The biggest problem, however, is not simply the distance itself. To understand why this is a suicide mission for the species, we have to establish the rules. If we are going to attempt intergalactic travel, we need a clear objective. We are sending a human spacecraft from Earth to the Andromeda Galaxy. There are 3 non-negotiable rules for this mission. First, the passengers must remain alive. Second, the spacecraft must survive the journey without being shredded by the vacuum of space. Third, we must be able to slow down after arriving. It does no good to fly through the galaxy at a fraction of light speed only to overshoot it and vanish into the void. We are ignoring magical teleportation or unexplained technology. We are sticking to the physics we know. Throughout this journey, we will compare several propulsion systems, and while one theoretical method could shorten the experience for the travelers dramatically, it creates an even stranger problem that defies common sense. We dream about this because Andromeda appears closer than it is. It is our nearest massive galactic neighbor. However, nearest in space means something different than on Earth. The 220,000 light-year galaxy is huge. Finding an interesting planet or steady star system is different from reaching its outer edge. We must choose a location before launching or spend another 100,000 years wandering the galactic periphery. Imagine the Milky Way as a dinner plate to visualize this cosmic distance. Andromeda wouldn't compete at that scale, about 25 feet distant. Between the 2 plates is a horrifying 3-dimensional map of empty interplanetary space, so perfect it makes Earth and Mars look crowded. First, try our most obvious option, using the fastest technology available. The fastest human-made object is the Parker Solar Probe at 430,000 miles per hour. Launching a crew in a ship at such speed would take billions of years. It takes almost 4 billion years to arrive. By the time the ship reached Andromeda's outskirts, the sun would have eaten the Earth, our solar system would be a graveyard, and humanity would likely be extinct or transformed. In addition to being slow, ordinary rockets fail massively. Compared to the universe, they're immovable. Perhaps we should rethink tactics if speed is a problem. Join the generation ship. An isolated civilization traveling the stars for aeons. This ship's inhabitants would never see Earth or the Andromeda Galaxy they are traveling toward. This ship must be a closed-loop ecosystem that provides food, medicine, education, and governance for millennia. Genetic variety must be carefully managed to avoid population collapse. A major mechanical breakdown or societal uprising could end the expedition. The ship would have to last longer than any human civilization on Earth. Imagine asking 1,000 generations of humans to live in a metal box for a mission selected by ancestors they never met and whose language they may no longer know. Even if we constructed a secure society, they would face a nearly undetectable threat from Earth. This brings us to the interstellar dust problem. In the space between galaxies, we often think of a perfect vacuum, but it isn't truly empty. There are stray atoms and microscopic dust particles scattered throughout the void. At the ordinary speeds of our current probes, these particles are manageable. But if we want to reach Andromeda in a human lifetime, we have to travel at a significant fraction of the speed of light. At those speeds, even a microscopic grain of dust becomes a kinetic bomb. Impacting a speck of dust at 90%, the speed of light would release the energy of a high-yield explosive. Furthermore, radiation exposure rises dramatically as the ship collides with stationary protons, turning the front of the ship into a radioactive furnace. To survive, the spacecraft would need massive shielding, perhaps kilometers of ice or lead. But more shielding means more mass, and more mass requires even more energy to move. The faster we travel, the emptiness of space becomes more dangerous, not less. Near-light travel is the most interesting realistic physics option. Einstein's theory of relativity says nothing with mass can attain light's speed, although we could approach it. A ship traveling at 99% the speed of light causes time dilation, which is exciting. From Earth, passengers would have a shorter journey due to time relativity. The crew may feel like they've traveled 50 years to Andromeda. They could leave young adults and return as seniors. This is where the theoretical method's odd difficulty arises. Earth would have aged 2.5 million years while the crew aged 50. No one they knew would remain. The civilization that sent them would be forgotten. Relativity moves time, not makes the journey easier. What energy might push a human spacecraft to those speeds? An incredible amount of energy is needed. As an object approaches the speed of light, its relativistic mass increases, requiring more energy for each minuscule speed gain. To accelerate a modest city-sized ship to relativistic speeds would take more energy than humanity has ever created. That's only half the issue. You must slow down at the Andromeda Galaxy. You require as much energy to slow down as to speed up. If you don't have enough fuel to flip the ship and fire the engines in the opposite direction for decades, you'll fly through Andromeda and back into the dark void at light speed. Fuel adds mass, so you need fuel to carry it. Beyond energy physics, biological and engineering restrictions block us. Our bodies are weak. We must accelerate at a safe 1g, similar to Earth's gravity, to avoid injuring or killing passengers. This would take years of immaculate engine reliability. Waste heat kills silently in space. Such powerful engines emit massive heat that cannot escape a Hoover. Every ship repair system would need spare parts and mass, and the spacecraft would navigate alone. Earth provides no real-time aid. A radio call for aid would take 2.5 million years to reach home, and the response would take 2.5 million years. Could suspended animation help? Hibernation could save food, space, and mental energy. However, humans cannot be frozen and awakened safely. Even if we could, cells and digital data degrade over millions of years. As sleeping passengers' DNA was progressively shredded by cosmic rays, the ship's autonomous systems would have to sustain the ship for longer than documented human history. Imagine the computer waking everyone up halfway there to discover the life support failed a millennium ago. Navigation is another issue. We see 2.5 million-year-old Andromeda. After that light departed, stars and planets migrated dramatically. Current targets are predictions, not guarantees. The travelers may find a dead star system or a completely different environment from Earth. The crew would be a detached island of humanity from another time. People commonly question about warp drives and wormholes. We don't know if these are usable, but they appear in Einstein's equations' mathematical solutions. Keep a wormhole open may need unusual stuff with negative energy density. something we have never seen. However, warp drive concepts like the Alcubierre drive are exciting for theoretical physics, but not for engine development. Creating a working interstellar spacecraft from a chalkboard equation is currently impossible. However, a twist. Waiting for Andromeda to reach us may be easier. Andromeda Galaxy and Milky Way are gravitationally attracted. At 68 miles per hour, they're closing in. Milkomeda, a large elliptical galaxy, will form from the two galaxies in 4 to 5 billion years. The night sky will change, but suns are too far apart to collide. The Earth may be uninhabitable by then, but the journey to Andromeda will be complete without leaving home. Why can't we reach Andromeda? Physics does not prove it is impossible, but modern humanity cannot do it. Cosmic distance requires technology, energy, and survival systems beyond our imagination. A successful mission would require us to change civilization. Andromeda is visible, but reaching it would need humanity to survive longer, travel faster, and construct better than before. It's a gorgeous, unattainable ghost in the sky for now,